Don't forget to like and subscribe. It's Jim Keller, everybody.
Welcome, everyone, to another episode of the Tech Poutine. This is episode number 24. We have an episode entirely about nanometers and angstroms and Foundry ahead of us. You may notice that I am alone right now. George had to step out. I'm not entirely sure when or if he'll be back, so you at least get me to begin with. But welcome, everyone who is joining. Please do drop a message in the chat. Let me know you're there. But it's been a hell of a few weeks. You probably realized we've not done a tech routine in a little while. That's because there's been a mixture of events and illness and lots of industry things. And it's interesting we do it now because we're ramping up into a very busy season for events. Like I say, we just had TSMC Foundry, we just had Intel Foundry, which are going to be the two main topics today. OCP had their European event in Dublin. I was actually asked to be on a panel for that, but it's there was a conflict with the with the other events going on. Coming up, we have a mixture of Computex in a little over a week. Both George and I will be there, and a few of the other tech YouTube scene will be there as well. At the same time, I believe it's Google I/O. It will be Dell Tech World. We've just had IBM Think this week. We had Cadence Live a few days ago. And they had Jensen and Lip-Bu on stage, because apparently designing chips is a big thing these days. And you know, from my perspective, it's been a really dense time. We're about to go into, like I say, Computex. We can talk a little bit about Computex during the show. It's going to be interesting this year for people who know, followed last year, for example. So we're going to get some interesting stuff's going to come from Computex this year. After that, we're going into VLSI, which is an IEEE event about chip design. That's going to be about manufacturing and circuits. If you do follow the IEEE events through the year, we have devices and we have circuits, and VLSI is kind of the one of the conferences that joins both together. So IEDM for devices, ISSCC for solid state circuits, and then VLSI just brings that together. That's going to be in Kyoto. I will be there, which will be interesting. And then there will also be AMD's Advancing AI event going, I believe that's June 12th, where we'll hear about their next generation of AI chips. So yes, George is hiding. I'm hoping he'll be back soon, because I know he has a bunch of opinions to share this week about GPUs, especially. Last couple of days, I've been actually taking some calls from journalists ahead of Computex. Them asking me what I'm expecting to see, what I'm expecting to hear, what all the different companies are doing, and whether the show is still relevant. Spoiler alert, it still is. It very highly is. And so just letting people come in. Small plug, we have new merch on the merch store. We're trying a new design. I do want to bring this up because I find it absolutely hilarious. Before we begin, be that one. We have a new T-shirt. It comes in two forms, whether you want it on the front or the rear. This keynote could have been an email. Something I came up with at the Intel event we're going to discuss today. And not because the keynote was boring or anything, just a play off words. And I thought that was ridiculously amusing. I've done 2 versions of this T-shirt. Mine is already in the mail. The thing is, I've gone for this one. This is the one I'm getting. So it has the this on the back, but it has my Tech Potato logo on the front. And that's purely because when I'm in a meeting, I don't necessarily need this keynote could have been an email when I'm on my T-shirt in a meeting when I'm speaking to a client, or if I'm at an event. So in order just to not be abrasive, this is the one on the back. So this is, I like this. We want to do more designs like this as and when we have more ideas, get more chips. Have to do a series of favorite chips in the industry. So as for the show, yeah, we're going to be speaking about the Foundry events. We've got some die shots of the Switch as well, and yeah, I like talking about chips. So let's get into it. Let's go into the main show. So I have a script now. We actually prepared this one. I just realized my third monitor is being weird. Yes, 3 monitors, because apparently a teleprompter counts as a monitor. So, hi everyone, and welcome to the Tech Poutine weekly-ish podcast from More Than More. I'm Ian Cuttress, also known as Chips, and my co-host George, who isn't here today, isn't here yet. I'm still waiting for him to sign in. Is Cheese, and if we had a guest, there would be Gravy, and then we'd have a full Tech Poutine. Right now, you're just having Tech Chips. That's fine because we all love chips, right? Also, if we had a sponsor, this is where we might put it. If you're interested, please do get in touch. We also accept and read super chats out on the air as long as they don't demonetize the channel. And if there's time at the episode, there'll be questions. And because you get me, you get all of my apparent knowledge that people seem to pay for these days. But it's fun times, and so I hope you enjoy the show. And the first topic is going to be, let me just bring it up here. I did have everything prepared, honest. Yeah, let's talk. I need to bring this over to the other. Oh, yeah, my teleprompter software has decided to crash. That's fun. Let me present this screen. Okay, that didn't work. Let's just go entire screen that way. I run lovely 3x2 monitors, so everything that's 16:9 really hurts. So TSMC held their tech symposium. This is their once-a-year deep dive into their Foundry offerings and Foundry roadmap. Full disclosure, TSMC did commission me to do a video about this event. It is still in the being approved stage. We've gone through it back a few times. So that video should be coming out on the channel next week. This is going to be essentially a similar run through, but I do hope you go see the video that does come out on the channel. But ahead of the event, we got a briefing from Kevin Zhang, who I have interviewed on the channel. And the best part of that interview was the first question I asked was about the future of Moore's Law. I asked him, does it matter? He said he didn't care. He said that for a good reason, essentially saying, regardless of what Moore's Law says or doesn't say or what you interpret it to be, we're still moving on. We've got a video actually that's already recorded in the editing suite about the future of process node technology, all the way out to 2039, based on a recent roadmap update from one of the research companies called Iambic. It will be I did a video very similar to it 2 years ago, and that was the roadmap up to I think about 2033. So we get to put a few more bits on the side. But as for TSMC, this is their tech symposium, a selection of their briefing slides that we're going to go through. So general everything. AI is going to go everywhere, so we're going to be applying for everything. That's great. This is an interesting slide. This is talking about where semiconductor revenue is going to be. If you've been following, especially Lisa at AMD, but also a few other companies, they're talking about how the semiconductor market is going to reach $1 trillion by the end of the decade. So we're talking about silicon, memory, packaging, supply chain, and just in terms of semiconductors. So ignore software for a second, just semiconductors. And TSMC had this graph showing us, how do we get to over $1 trillion by 2030? Well, here's the forecast, but also how many units does that mean? It's one thing to talk about numbers in terms of dollars, but also numbers in terms of chips matters. So we have, at the bottom right now, we have 5 million units of the data center AI accelerator. A good chunk of those are Nvidia, but a lot of other players as well. And then we have 50 million units by the end of the decade. This looks like a yearly number. Okay, that 5 to 50 almost sounds like a yearly number, but as I go up to AI PC, that's talking about 100 million units to 280 million units. That sounds like a yearly number, and I say that because the unit rate for PC and desktop and notebook, that whole market, is about 260, 270, 280 million units a year. And the idea is that eventually all of those will have some form of NPU, therefore they're an AI PC. The one that confuses me, however, is smartphone. Smartphone says 200 million units going to 1 billion units. Now, 200 million, if I'm right in saying that market sells about 150 to 180 million units a year, it may even be more than that. But that's been a very flat market for a while now. It's saying 1 billion. Yeah. I don't think 1 billion units a year, 1 billion units total, maybe. And then we have AI, the AR, XR, robotaxi, humanoid, comparatively smaller units there. If you can see my pointer here, the humanoid robotics thing, that's 2.5 million units. Whether that's chips or robots, it's probably chips. Humanoid robots by 2030. How much do you think that's going to be? But the way that from TSMC sees it, this is their breakdown in terms of where the revenue is going to come from. These are, if you ever dive into TSMC's revenue numbers every quarter, these are the 5 areas they break down their revenue, and they're saying this is what they expect the revenue split to be in 2030. The thing is, there's a lot of talk of obviously the US market and tariffs. So even though most silicon is manufactured in Asia, it's mostly consumed in the US. So how big is that market? Today, TSMC is saying it's a $250 billion market. By the end of the decade, it's going to be bigger than $500 billion. They're obviously building fabs in Arizona, and they're building up the supply chain in the US to do a lot more onshore manufacturing. However, with everything that's going on, who knows? So yeah, that's going to be interesting. It's 500. When you hear about Stargate and 500 billion, that project's with Larry Ellison and Masasan of SoftBank, and then you hear about TSMC investing 160 billion. Then you hear about TSMC 160 billion. Nvidia announced 100 billion for their supply chain. There's also it says US semiconductor industry. In Mexico, there's a lot of nearshore, server manufacturing that happens. Foxconn, Wiwin, all those players all have places not only inside the US but just across the border in Mexico. So there's a lot of money going around. And again, this is just hardware. This has nothing to do with software. But ultimately, this is TSMC's roadmap, going out from 2020 all the way through to 2028 using their node names, because companies have their own version of node names. And there's a slight difference here to what we've seen before, but we'll go through that. And the key part here is where we are in 2025. We've got companies building on N3E, N3P, N3X. So all the TSMC N3 is basically P and X that's being produced today. We have N2 that's being discussed today. You may remember last time on the Tech Poutine, we spoke about AMD now has some of their Zen 6 chiplets, first spins coming out on N2 over in Taiwan. And there's that presentation image with CC Wei and Lisa Su with one of the wafers. So that's coming down, first gate all around. We'll get into that in a bit. And then after that, we have the P, the performance version of N2P. We have A, the automotive version of N3A. And then we get into the A16, A14. And then there's an N2X as well, which has a more high performance version of N2. And at the bottom here, we have the cost-focused platform. So N4P was the cost-focused platform for N4, or it evolved from the performance down into the cost. And then we have N4C and N3C. This is more, as it says in the bottom left here, for mid to low end mobile consumer. Think about all these sort of $200 to $400 smartphones. So, okay, we're going in reverse order for this one. So the most advanced technology, the headline of the event was A14. And A14 is TSMC's second generation of nanosheet transistor, nanosheet being their marketing name for gate all around. And the whole idea is that it's another full node jump from their first generation of gate all around. Difference here being is that second line here, this NanoFlex Pro technology. So NanoFlex just means the ability to adjust the gates inside the transistor. They're saying here a good development progress with yield of plan and device on track, which is a normal thing that a lot they say. And production is targeted for 2028. But this is the version without backside power delivery, this add-on feature. And that version is coming in 2029. And they have some numbers here versus a standard N2 process. More, so first gen to second gen gate all around, you're getting up to 15% better speed for the same power, or, which I think is critical here, 25 to 30% reduction in power for the same speed, with 20% density increase going from N2 to A14. So we're going to start hitting about 500 million transistors per square mil, and that's pretty exciting. Then we have A16. If we go back to our roadmap, A16 is the end of 2026 node here. And this is the best way to put this is A16 is N2, but with backside power delivery with super power rail. So you get the benefits of N2, but you get the power rail benefits. Now, because backside power delivery, power rail is a new technology, it's been in the IEEE conferences for, I don't know, 5, 6, 7 years at this point, then getting to volume is part of the difficulty. And we've heard Intel say this as well. But in terms of just the uplift from standard N2, it's a bit more modest just because it's not a new transistor technology, but it's just a new way of delivering power. So up to 10% performance at same voltage, up to 20% better power at same speed, and almost another 10% chip density. As it says here, second half of 2026. Now, N2, the first generation, so this is what's going to compete with 18A, Intel's 18A. This is the first generation of the nano ribbon technology. Sorry, just being a little bit distracted. the point here is that the benefits of gate all around is you get a significant jump in the transistor, right? This is why we get up to 18% speed improvement, up to 80, double that in terms of power reduction, same speed, and a 20% logic density. Yeah. The what was I going to say here? Yeah, so N2 is a family. N2P is going to be what's going to be mainly used in production. This sort of second half 26, and this is why we get these numbers down here. So N2 will be used as the name for the family. N2P is a thing. Then N2X, which is going to be the more extreme version. This is where they're going to have tighter corners and more VT options. Is going to be a few months later with the 10% frequency. This thing here, the 256 megabit SRAM average yield is greater than 90%. This is I've said this before, this is a little bit of a weird metric. Because mid last year, I think they said this was 80%. Now they're saying over 90. If you know the density of their SRAM, you can work out what size chip that would be. And then you can work back to the defect rate. And it typically doesn't sound great when this is the number you're putting out. If you know how to do the math backwards, the defect rate sounds really high for what it is. However, TSMC have been showcasing an SRAM block as its yield provider. I've been saying for a while now, yield without a die size doesn't mean anything. We also have to think about what the performance of the SRAM is, and we did. I think we did a Tech Poutine on that a few ago, doing comparison about SRAM. So go check that one out if you want to hear about the research papers at the IEEE conferences about the SRAM comparison between TSMC and Intel. Back here. One thing that TSMC wanted to highlight is keeping track of tape outs. So this is the NTO, number of tape outs. And this just means partners who have gone all the way through from design, Verilog, RDL to GDS2 to actually producing a chip and making it go through the production line. The number of tape outs just essentially showcases how much interest there is. Some of these tape outs won't make volume products, or they might be test vehicles. But what TSMC is saying here is that they're seeing a 4x uplift, 2x in the first year, 4x in the second year, compared to the 5 nanometer, which essentially was a mature FinFET, but just as a die string. N2 being a new technology to have this amount of interest is impressive. The other thing here they said is HPC AI products. Normally, high performance computing, again, GPUs, smart, may start, not smartphone, but GPUs and ASICs and that sort of thing. They usually get involved with a process node technology 2 to 3 years after it's, PDK's been available, not on day one. They are saying now that those companies are getting on board a lot earlier because they need to use the nodes to drive their product roadmap. And then lastly, on the nodes, an update on N3. So we are starting to see some N3 silicon hit the market now. The thing is, N3 is going to be split into essentially 4 different variants that actually make sense. We've got N3P, which is the one that's in volume production right now. N3E was kind of like the early one. N3X, this one at the top here, that's going to be used mostly for client and client chiplets. We've got an A version for automotive and a C for cost-focused markets, like I say, the mid to low-end smartphone sort of thing. It was asked in the Q&A what the C actually means in terms of cost, and we were told from when you buy wafers from TSMC perspective, it's about 10%. However, TSMC expects, because gate all around, because N2 with the nano ribbon will be a slight cost adder to production. It's expected that N3 will be a long-lasting node because of the price performance benefits it provides. So N7, for example, has been a long-lasting node, and the derivative N6 as well. So whether N5 stays around for long, or and N4, I've always had the impression that they kind of sound like they all are. Though TSMC was keen to point out that N3 definitely will be, and the variants therein. Then we get to speak about packaging technology. Now, this isn't necessarily the packaging conference for TSMC. That's more like OIP, which is later in the year. However, they went through, they're offering SOIC, which is their 3D stacking on the left. And then you have CoWoS S, CoWoS L, which is more like the interposer and chip-to-chip connectivity. We've seen this before. The key thing here, there's going to be a couple of key things here that we'll get into. I'll bring up this question from Cybot. Where is N3B on the chart? So N3B was like a minor early thing. You're not going to hear much about it at all going forward. It'll be one of those things that if it has a feature that a particular customer wants, they can go to it, but it's not going to be like their promoted lines. So, okay, so packaging. This is this is one of the big ones, right? This is talking about how big can we make the substrate, which is the green thing, and then how do we connect all the chips together on that substrate, and how big do we make the interposer, which is the gray thing, in all of these. Now, what we're seeing here in these chips, you have the compute SoCs in that sort of bluey green color, then you have the HBMs in yellow and the IO, in red. And the whole thing is, how can we get to wafer scale, which is this thing on the right offering 40x. So on the left, we've got an 8 HBM chip on an 80 by 80 substrate. I think I pulled this chip out last Poutine, but for those of you who didn't see, this is a MediaTek ASIC they did for Cisco. It's a switch chip from 2022, and this is the 80 mil by 80 mil substrate on the left. This is the largest package that they made at the time. So a lot of effort goes into making large packages. You end up with large substrates. Here they're saying the substrate is 3.3x reticle. This isn't that because it doesn't have HBM on it, but it does have IO on the edge of the ASIC as separate chiplets. Sorry, I don't have autofocus on my camera, so I can't do a quick zoom in. If you search for Cisco Quad Peaks on Google, you'll see a picture of it. But the whole idea is that you'll go from this to bigger chips. And those interested for seeing the back again, for those who didn't see it last week, it's about a 10,000 LGA land grid array pads on the back, and this goes into a switch, and then you stick your Ethernet ports inside or whatever. And the whole point here is that for this for the second one on here, we are already starting to see designs of this ilk. Rubin, for example, looks kind of like this in the CoWoS. Then we have the 4-way chip. If you have seen the thumbnail to this live stream, there is an image of something looking kind of like this from Intel, but just showcasing that this is the direction that the industry is going in. And then we get the full system on wafer, which is the Cerebrus stuff. And I've got a Cerebrus thing here. So about that big. I believe this is this the scale? No, that's less than 12 inches. Anyway, the whole point here is you have a wafer as big as a chip as big as a wafer as big as your head. That's usually the advertising that I put around that. But the point here is that it looks more, this is almost one big monolithic die built into the wafer. what we're seeing here on the right with SOWX is that you have multiple chips, so multiple compute chips, multiple HBM chips, multiple I/O built onto the wafer, and then you have all your connections underneath. But they're saying that more customers are going to start using this technology. Right now, we have Cerebras and Tesla; they're the big two, but we'll get more down this route as we go on. Then in terms of actual chip-on-chip technology, this graph is a little misleading because it looks like, top die is N3, bottom die is N4. The way it was presented to me was it's more like any die can be on any die. It just depends what you want. And what TSMC is saying here that, when you do, so with Vcache, for example, if you have, say, like an N6 on an N6, this is like the one in the bottom left here, right? The size of that die is 0.4 reticles, and the size of the connections, the bump pitch, well, they're not bumped, but the connection pitch is 9 microns from connection to connection. That's coming down over time. So right now they're saying that in production they have 6 micron pitch. They wouldn't tell me what product that's in. I'm not sure if that is AMD's latest or not. AMD hasn't said. But we are moving down to 5 micron and below over the years. And eventually, they're saying next generation stacking of A14 on N2. So N2 is the base die, A14 as the top die, will be ready in 2029. The third area of presentation is going to be on power delivery. So if you're following this industry, you'll know that chips be crazy hot. And I'm not necessarily speaking about the GPUs or CPUs that we buy. AI chips, upwards of 600 watts, 1,000 watts, 1,200, I believe Blackwell is rated at. And the idea is that they're going to go to 2 kilowatts. Now, I've done videos about TSMC's research in cooling some of this stuff, but that was artificial dummy load on a heat plate and how to cool it. You also need to deliver that amount of power in a chip this big, right? So how do you do that? Well, you need the technology platform for tomorrow, the world of tomorrow. And this is how it goes down. So we've spoken about 3D stacking here at the top. We've got memory, high performance memory on the side. We've got interposer in the middle with some of the components that are going in, silicon photonics on the side. And if you follow the channel, we've been doing a bit of content recently about co-packaged optics. Plenty of rants here. I think if we go to this slide, we get more into the power delivery here. So normally when you look at the bottom of a chip, and let me get a different chip out this time. See if I can get a. Okay, yep. Okay, a Xeon Phi, because this is a large chip and maybe you might be able to see something. Even if you Google like Intel CPU or AMD CPU, you'll notice that at the bottom you'll have bump pads and pins, but you also have like decoupling capacitors on the bottom, and these are slightly raised. The idea here is that you can either put the capacitors on the package where they take up space, and if you have a look at the front of a CPU, you might see some capacitors on the side, or you put them in the package and you can actually put them either in the substrate or in the interposer or on the chip itself. The thing is that limits their utility. It also can create some interference. And the idea is that you probably want your capacitors to be super thin and super efficient, and you don't want them to interfere it. So where's the best place to put them? And we've seen some of this stuff from Intel has been a bit vocal about what they're doing in the space with their voltage regulators and stuff. But TSMC is saying they can now do power management controllers in the interposer. So normally to date, we've thought about interposers in terms of passive interposers. It's just a big hunk of silicon with a bunch of wires helping connections. You can also have active interposers where they have logic and they have things like power management controls on the left, or on the right, we have deep trench capacitors. These help with the power delivery, help with the isolation. In some cases, it help improve frequency up to 30%. But the whole idea is that now you have an interposer that actually has active circuitry. If you were putting a full GPU inside, yeah, you would have logic on logic and have to deal with thermals. This isn't like that enough. But you can have deep trench capacitors on the side, or you can have them integrated in the interposer. This is part of the CoWoS L family of packaging. So this is an organic package type and this is technical like an RDL layer. L stands for layer, and as Ryan says, yeah, just shove a 12-volt high power connection to it. But that way the connector melts, and then you have a protective plastic thing around it. I say that, and I have one of the connectors. It's not a melty one yet, but this is first gen 12-volt high power, so that's fun. And then we get into more things about, well, AR uses how many different silicon technologies and how many come from TSMC. And then we get the future of robotics, which is more application level, not silicon level. And that was the tech symposium, which was fun. It's unfortunately I wasn't there in person. I had to watch it. There is a tech symposium in Taiwan next week, which is essentially going to go over the same thing but be more local. And then there's one in Europe on the 27th in Amsterdam. I will be at that one. And again, that will be more focused towards the European market and what they can offer for the European market. We'll get to spend time with executives. They're being a bit more open this year, because previously you got to go to the keynote, you got a press Q&A with an executive, and then you weren't allowed to go to anything else for the rest of the day. It was customers only. It sounds like this year they're opening up the customer only sessions in the afternoon to press and analysts. So that should be interesting, because we might get a bit more information there about the deeper integration with customers that they have to do. I'm always interested in learning more about how Foundry works with partners, about the state of PDKs. They didn't go into PDK stuff. We're going to PDK stuff with the Intel side of things. Hold on, let me just check something. So I heard something beep. Yeah, okay. Random messages on LinkedIn. That'll be what. And yeah, that was so that was TSMC. I think we need to hear more about their build out in Arizona. Need to hear, because again, there's been a mixture of stories about how people don't want to work for TSMC in Arizona because of the 996 type, which is 9 a.m. to 9 p.m. 6 days a week. That sort of lifestyle that Asia typically has, compared to 9 to 5 days a week that most of the US has. They have started producing N4 silicon, N4P silicon, I believe it is, and they're going through validation of AMD's Zen 5 chiplets there in Arizona, and Nvidia are also doing the first tape outs of Blackwell at Arizona. So if you want a made in America chip, and as Ahmad points out, packaged in Taiwan, this is the whole thing about the chip industry and about chiplets in general. If you're making stuff at different fabs, you have to then bring it together at a packaging facility and then ship it somewhere. So your chip may have been twice around the world before it gets to you. And And then all the other chips in your notebook may have been twice around the world as well. So now you have a device that's been around the world 50 times if you count up all, how far everything has traveled inside it. It's last time I spoke to Dr. Kevin Zhang last year, I did ask TSMC, are you going to be bringing advanced packaging to the US? And at the time he said no plans. However, the latest $100 billion announcement we are now understanding includes some packaging, test and validation facilities. Captain K says that they have advanced packaging partners, but that's more the OSATs that help do part of the process, not all of it. Some of it has to be done in Taiwan. It's important here to not get confused with some of Nvidia's partners. So TSMC essentially offers two things. They offer manufacturing and packaging services. However, some companies use external packaging services. So like ASE and Amkor and companies like that. They do have facilities. I think Amkor is actually mostly in Korea, and they just recently announced that they'll be doing some more, that they'll be building a facility in the US. But I think the timeline for that is 2028. It's that sort of thing. Is it Amkor? I think it is Amkor. Kevin K also says, SPIL also has facilities nearby. So Gregan asks, Forksheet transistor will be skipped. Now, I'm not sure if it will come up on any of the slides from Intel, but so for those of you who aren't aware, a Forksheet is normally with gate-all-around and nanoribbon, you have your 3 or 4 ribbons, and they almost stand alone. The idea is that you can put an isolation layer in the middle, and it all acts as 2 transistors, and we call this a Forksheet. I've been hearing from companies that they're not interpreting Forksheet as an independent process node technology. They're thinking that Forksheet will become a variant of gate-all-around rather than its own pathway. Well, as in, it will be a fork of gate-all-around rather than the evolution of gate-all-around. Yeah, so Forksheet is a forked technology, if that makes sense. When back-to-back tunnel FETs over time, like I say, we have a video that's edited about the future of transistor technology going through Iambic roadmap. I suggest you wait for that. It's in the editing suite right now. I need to do a pass on it. So after this, and still no word from George, so he's still busy, it would seem. But he hasn't got back to me. It means that, I hope he's okay. Let's go on to the Intel Foundry event side of things. It's at this stage. So Foundry, this event I was actually at. This was done in the San Jose Convention Center in San Francisco. The funny thing is, it's the same venue where Nvidia held GTC back at the end of May. The GTC banners around the area on the high street, on the main roads, hadn't been taken down. So you had this Intel Foundry event and a lot of GTC banners everywhere. Some people questioned whether Intel needed a Foundry event. One, brand new CEO. How much is he going to say there's going to be a change of direction? They've also gone through several changes of leadership in the last couple of years. If you've been following them, I think they're on there now, their 3rd or 4th person in charge. since Pat Gilson came in and started talking about IDM 2.0. However, the event itself was really, really good. The keynotes we had and the one-on-one conversations I had made it very well worth attending if you have the opportunity. You got to understand a lot about what Intel's strategy is doing, but also it level set a lot for a bunch of people in the room. So this person here that you can see in the slide, this is the new CEO, Poutine. He had been in the hot seat 5 weeks by that time. Unfortunately, I got to the room late, so I didn't get a front row seat, which made for some interesting images, but what have you. And so Intel, going through their strategy. Lip-Bu kind of just gave the highlights and then let the other people talk. 18A, 14A is obviously going to be the next leading edge and stuff. We'll get into that as well. And I think these slides are in a weird order, but this is Naga Chandrasekar. He's the head of new head of technology over at Intel Foundry, talking about how Intel 4 is Intel's first EUV node. While TSMC N7 has been out for 3 years already. Intel 3, however, is where Foundry customers are going to come in. It's going to be the leading edge technology node in Europe. This is what they're doing at Intel Ireland. And then we have Intel 16, some of which will be made in Ireland as well. This is kind of super high level, but 18A is meant to be the volume. And there'll be some differential. I'll get into some of the specifics, but 18A as a family is meant to be the main deliverable for Foundry customers. And then they've got this partnership with UMC called 12. Some of the marketing changes. They call it Intel 12, but here it says 12 nanometer, and we're going to get into that argument all over again. But the idea is that Intel has all the Foundry equipment. UMC is going to build a PDK, which is the process development kit, what you use to make sure that your silicon actually, you can build it and it works. It has all the design rules. And this is based on all of Intel's old 14 and 10 nanometer equipment. And then UMC is the customers it has in Asia and in the US and in Europe. If they want a more advanced process node, then it's going to be using Intel Foundry through the UMC 12 PDK in order to do it. And they're going to be developing and ramping technologies of 12 in both Oregon and Arizona at the same time. What they did say at the event is that previously Intel's method of bringing up new nodes involved, let's make the node work in Oregon first, because Oregon's their big facility. It's if you see my videos about touring fabs, pretty much all of them are in Oregon. The idea is that let's get the process node to work there first, and then Intel does what's called a copy exact, which means that they'll take the layout and the plan of that node and go put it in a different foundry like Ireland. So for Intel 4 and 3, for example, they got it working in Oregon. Once it's working in Oregon, then they move it over to Ireland for mass production. And the idea is that while they're getting it to work, they can build out, the fab floor and the facility and start ordering. The thing is, between development and high volume manufacturing, you end up with a large delay. Now, Oregon itself does do a lot of manufacturing. Thing is, if you're building a test node to get it to work and then start using that test node for high volume manufacturing, the idea of it being a test node is you may not use it for that node in the future. And so in order to avoid some of the overlap, they're now doing, instead of copy exact, they're doing something like copy together. So they're doing that, or copy joint. So it's a joint development in both locations at the same time. and engineers will go back and forth to ensure that it works. So that was one key change that I found in Intel's strategy at the event. We got an indication of Intel 18A and Intel 18AP. For those of you unaware, 18AP is going to be like N3P, essentially the slight addition in performance per watt in power. What it does is it adds more VT options to the PDK. It tightens some of the design kit rules, especially at the corners. So you get a small performance enhancement, but they're characterizing it essentially as a process node step. In the past, when we had like 90 nanometer, 113 nanometer, that sort of small step might have just been rolled into the old node and we wouldn't have heard about it. But the point here is that Intel has, well, one of the metrics for process node health is defect rate, this concept of D0. This is the number of defects per square centimeter that a wafer has, physical defects. You could argue that you could just say the number of defects per wafer. A modern TSMC N7 or N5 wafer has around 30 defects per wafer, 30 physical defects per wafer. Sometimes those physical defects are in areas that don't matter, or that they're in redundant areas with failover. So the effect of the defect is essentially zero. The other side of yield is parametric yield, which is more to do with frequency and voltage and binning. But we're not talking about that here. We're just speaking about defect density. And they're saying that this line here follows industry trends. But this is average defect density. You do have this concept of best wafer defect density. And they're saying that their best wafers today, because defects are random, their best wafers today are good enough for high volume. However, high volume is actually going to start at the end of the year once they've managed to get the average down. I think, so the idea being that, by Q4 of 2025, you get the average wafer will hit the defect density. If you manage to get a wafer that is defect free, typically that wafer gets pulled off the production line and framed. Even with, say, 30 defects a wafer on average, it's almost like a standard distribution, a normal distribution. There will be at some point a wafer with 0 defects, and then that usually gets framed and gets put in the CEO or the lead engineer's office. So we sometimes see those on the walls of Intel. If you ever get to go visit, ask to see the wall of wafers. IBM has a good one as well. They gave us some indication of where they are in the process. These graphs can be complicated without some explanation. However, what they're saying here is the frequency of a chip is related to the power leakage of the transistor, and the leakage transistor can run at a higher frequency but consumes way more power. And the point here is that they are hitting targets, or they're in the process of getting to target here. This is what's on the left. On the right, this is one of their SRAM cells, the high current cell, which is the high performance cell on the top, and the high density cell on the bottom. And they're saying that their SRAM cells are all meeting specifications in terms of performance. As Cyborg says, yeah, it should. I misspoke when I said normal distribution. It will be a Poisson distribution, technically. This is their roadmap, though they had a much better version of this roadmap without all the dark side. But the stuff on the light side here is all the new process nodes that they will be coming in the future. So we've mentioned, if you can see in the dark, Intel 4, Intel 3. Variants of this, 3T, 3E. We've mentioned 18A. This is the first power via backside power delivery process. And then we get into 2026 with AP and Intel 12. Then there'll be one thing new here that wasn't announced is that there will be variants of 12, likely to be called 11 and 10, but we'll get into that in a bit. Then we have 14A, which is after 18A, and this family will be the first high-NA EUV. And there is some differentiation here as well. So high-NA, the next generation EUV technology, requires a new machine. Intel has got a couple of them now. I think they said they've run through 30,000 wafers on their machines now. So, you know, they're currently in the process of enabling that technology in Oregon. The idea is that it makes the bottom layers of the metal layers of the transistor stack cheaper, because you only need to use we'll get to a slide later that I've definitely added in about what makes it cheaper and what makes it better. You can also get finer detail in your silicon. However, there will be regular EUV options. So you don't the thing is, if you want to go to high volume with any process, you need to make sure you have all the tools needed to enable that. So if we take the concept of TSMC's gigafab, a gigafab does around 100,000 wafer starts a month. Now, it means you need all the tools to start 100,000 wafers a month. A high-NA EUV machine right now is 100 wafers an hour. So if I put hours in a month, 730. So then that means wafers per month with one EUV machine could be 73,000. That doesn't happen. Utilization of that 100 wafers per hour is based on the ASML dose of energy you give it. And realistically, most fabs run at almost double that dose. So it's actually half that rate. And then these machines don't have 100% uptime. They have 80% uptime. So if we take that 73,000, divided by 2, because they're using double the dose, let's say 6,500. And then we say, let's say it's a new machine, uptime may have an issue. Let's say 75%. So you need 27,000 wafer starts can go through this. You're also doing, like, say, 3 metal layers. So you need to go through the machine 3 times. So one machine can do 9,000 wafer starts a month. So you need 10 machines for a gigafab. Right now, Intel has 2. They cost $354 million each. And this is why they're saying that 14A will have a regular EUV option, because if a customer comes in and just eats up all that volume, nobody else is going to get a look in unless they pay the higher amounts. So it's that sort of thing. Ahmad asks, what's the minimum amount of usable chips from a single wafer? 0. I mean, you can have a wafer with 0 usable chips. You can have a wafer that's 100% usable chips. Yeah. So and then that's a little bit of the high-NA EUV stuff on 14. And then we get other variants here on the right. Let's so 14A and 14AE. So 14A is the second generation ribbon FET. This is what we saw with A14 with TSMC. So we're going to have A14 versus 14A. I've already made that mistake wrong once in a thumbnail that I had to correct. Thankfully, that video hasn't gone out yet. But yeah, it's with the second generation, it's similar sort of numbers to what we saw with TSMC. The perf per watt increase of 15 to 20%, the around 30% power reduction, and the 1.2 to 1.3x chip density increase. Density is also a weird metric because you don't always use high dense transistors, and yeah. They're also saying here this third line here, Power Direct. Intel has a new version of Power Via they're going to implement on 14A, except they're going to call it Power Direct. I need to dig into exactly the details of that. I believe they've started presenting some of that stuff at conferences. Now, in terms of packaging, the two main names on Intel's packaging for the longest time now have been EMIB and Foveros. EMIB is for the integrated die-to-die packaging, and then Foveros is for the 3D stacking. And they now have more visibility into that roadmap. This is one of the good things about this conference is we saw a lot about the roadmap. Yeah. And joining us is George. Hey, George. So, hey, George. You're live and well.
Yeah, sorry.
It's all right. Just early in the conversation as we go.
Yep. Sorry about that.
It's all right.
Life happens.
So, yep, it is what it is. So, yeah, EMIB and Foveros. This is currently what's available today. On the left is your standard packaging that we see. You know, things like Xeons and what have you, and Xeon Phis. EMIB, they're die-to-die. They're currently on a bump pitch of around 55 to 45 micron. And then that has associated power. And then Foveros, you know, the 3D stacking that we currently see. We first version was in Lakefield, which was a 2018, 2019 product.
Yes, I believe it was 2018.
Yeah. And then
Sunny Cove core and 4 Tremont cores.
But now obviously we have Rapt Lake, Lunar Lake, Arrow Lake, all using Foveros. Going down in bump pitch, I believe they're Foveros 45.
So this is what always confused me about Intel's naming scheme is that is Foveros their 3D stacking technology or not? Because
yes.
Okay, but it's also their 2.5D stacking technology.
No, their 2.5D is EMIB.
But this diagram does not show a 3D stacking image.
No, it does. You see where it says active or passive?
Yes, but
it's the way to think about it is if you have one chip on top of another, like CoWoS, that's Foveros. If you have an embedded bridge in a substrate, that's EMIB.
So by that logic, then CoWoS is also 3D.
Yes.
Yeah. See, I don't like the in particularities of that. I would call Foveros S at the very least 2.5D, because to me that's what it's most closely related to cousin on the TSMC side, aka CoWoS is.
It's when we start getting more than 2 die stacked, Intel will call it all Foveros. TSMC will call it all SOIC.
I guess. Have you covered the lower pitch?
We get to that.
Okay.
Get to that. We're literally just going through the slides right now. Yeah, it's close up of the image. But these are the new additions. So one thing that Intel did well at Foundry is that they actually gave their naming scheme some proper vision as to what they're doing. So EMIB, they've essentially renamed everything that has EMIB today is EMIB-M. The new version is going to be EMIB-T. And the point is that EMIB-M previously was a dumb way. I'm not saying it's. I'm saying dumb as in it doesn't have any logic inside. It's just literally wires. It's almost like a passive CoWoS, but embedded into the substrate. However, there will be times in the future where you need to provide power through an EMIB connection from the substrate through the EMIB, or you might need the EMIB connection to have capacitors or inductors. So that's what EMIB-T is. It's a TSV version that allows connections to go straight through an EMIB. Then you have Foveros evolution. So now instead of just calling it Foveros, we have Foveros S, Foveros R, and Foveros B. Foveros S is essentially Intel's version of CoWoS S. Foveros R is Intel's version of CoWoS L. And the reason why that is because it's an RDL, redistributable layer, and organic package, except that Foveros is going to call it R, CoWoS is going to call it L. And then we have B, which is when you want to add EMIB to an RDL layer.
Okay, interesting.
So the B stands for bridge, but it's a bridge in an RDL layer. And you might think, why do you need a bridge in an RDL layer?
Mm-hmm.
A bridge, in an RDL layer, there are some things you can do in a bridge that you can't do in an RDL. So, we will get more information as time goes on, but this is one of the furthest ones out.
So moving on to Foveros Direct3D. Now, I just got messaged by Dom. You guys have covered TSMC already.
Yes.
So what's interesting to me here on the bump pitch is I remember there being a slide about a 6 micron or 5 micron bump pitch, and on the for Intel, and on the TSMC slides for the sub 9 micron bump pitch, they're moving to face. So I wonder if this is really not just Foveros Direct3D, but also Intel saying we're moving to face, which allows for smaller bump pitches, which of course increase the number of TSVs that you can have and the number of data connections. If I remember correctly, at VLSI this year, IMEC is going to be giving a talk about 250 nanometer TSMCs for face-to-face packaging.
So Intel is already productizing their Foveros Direct 9 micron.
Okay.
As in to be coming in a product. They are essentially skipping 6 and going straight to 5.
Okay.
And that's just a function of what R&D has been. So yes, that will happen. To your point about sub 1 micron connections, that's been in the IEEE conferences for over about 18 months now. It's not only about how small you can get the TSVs, but sometimes you'll have one TSV that's like, say, 250, and on the other side it will be 500, because then you have a wider area for connection, and it's all about how you do the overlap. And we always see the stylized images. The thing is, with some of this stuff, you have to deal with warping and thermals and how that changes, because these are bumpless bonds. It's almost like friction welding.
Yeah, and bumpless is the same sort of packaging that 3D V-Cache uses, right?
Yes.
So that's whereas for Lakefield and for prior Foveros products, they had bumps, just like you see in the images. Yeah.
As opposed to C4 bumps, which is the bigger stuff we see. Yeah. Yep.
C4 is substrate to chip usually.
Yes. And then we move on to co-packaged optics. This isn't something that Intel's necessarily it's spoken about, and then they mothballed their networking division who was meant to be using it, and then they showed off a demo, and then they've also invested in a bunch of CPO companies, and then they also invested in some R&D about pluggable optics in Scotland, of all things. It's been a bit difficult to follow exactly Intel's CPO strategy. However, they did outline this slide showing how they've got a solution for direct fiber attach, and I think most people have it now. The second generation CPO from this perspective, if anybody's familiar with my diagram of CPO, this probably means more like third generation. This is with the optical package connector, and then on the bottom right here, we're talking about sub 1 picojoule per bit, but we're now talking about having your photonic connections connected to the XPU via chiplet, and then going up out of the package, and then being redirected horizontal to the package, rather than just coming straight out the side like it looks in the first gen CPO and second gen CPO. 3D photonics in this case goes out, up, out, and that's 3D. Apparently, I actually spent in the last couple of weeks some time with Celestial AI, so I understand their solution a lot better now. There are some commonalities. So yeah. And this was a wafer of I believe it was of 14A, one of the test vehicles. Yeah, and that's a very test vehicle pattern.
It looks very SRAM-y.
Well, no, as in some of this will be logic, some of this will be memories, and some of it will be IP. They'll carve it up and test to see if it works. That's why it doesn't look as regular as a chiplet would. It's almost like a multi-project wafer or an MPW. Yeah, and then this was an interesting thing Intel brought up as they visioned the future. I'm not sure if you saw this, George.
I did. I wasn't completely clear. Is this like actual things that are planning to become products, or is this just imaginings?
A concept of how things come together.
Okay.
And I wanted to talk through it. So, Intel. Let's start in the center. So we have a base die. So this is a compute-based die that the ASIC itself made on 18
die, so to speak.
Yep, made on Intel 18A-P, so their 18AP process, but the TSV version, which means it supports through silicon vias, which means you can use it for stacking.
Okay.
So this is the 2028 18A, right?
Okay.
This doesn't need to be monolithic. I'll just put that up. This could be different. Then you have I'm not sure if you can see it clearly here, but between these two purple, so you have an EMIB-T, so that's your in-package bridge, but T because it supports TSVs. You also have one here on the right hand side. Now in purple is UCIe A. So using a standard physical protocol, the electrical protocol, or the logical protocol could be anything, but UCIe.
Yes, the
physical and electricals.
So for the audience who doesn't know, UCIe, the actual pinout comes in two flavors. It comes in UCIe S, which stands for standard packaging, and UCIe A, which stands for advanced packaging. Now, usually UCIe A is 4 times the link width. So it's a 64x link instead of a 16x link. So here, what they're showing is using their EMIB, you have the electrical protocol and the PHY, because UCIe also has PHYs, but you can run anything you want over that PHY. So for example, AMD's Infinity Fabric XGMI or GMI runs over PCIe PHYs.
Yeah.
You can run your own protocol over this logical protocol, but the electrical and analog standards are UCIe.
Yeah. And A is meant to be for higher bandwidth connections as well.
Mm-hmm.
Yeah. A for advanced packaging, but A for advanced performance as well. And then on this left side here, you have things like a non-coherent fabric, so a DPU, perhaps an optical engine. You have PCIe Gen 7, other IOs, other high-speed SerDes connections to connect to other things, what have you. The idea is that's the off-chip IO.
And one last thing I think is interesting here is the LPDDR5X.
Hang on, we haven't got there yet.
Okay.
I'm talking about this thing on the left here.
Oh, I thought you were about to move over to the next slide. Sorry about that.
No. And then what's interesting here is Intel is also saying that for chip to memory connections here, we're also using UCIe rather than something else,
which is interesting.
Yeah, I wasn't.
Considering just the amount of bandwidth that a PHY would need to cover in that area, it's interesting that they're saying UCIe.
So UCIe 2.0 today is a 32 gigabit per second technology.
Yes.
So I think Synopsys has like a 36 gig version, or Cadence has a 36 gig version. Thing is, HBM5, it's roughly going to be about 2 terabytes a second per module. How many 32 gig UCIe connections do you need for 2 terabytes per second?
So using the standard UCIe at 64 links, that means you would need 8 bidirectional links. So that would be 512 lanes of UCIe per HBM5 package.
No, but that's 32 gigabits per second.
Yes.
Versus 2 terabytes per second.
Yes.
So you need a by 8 multiplier as well.
Yes, I've divided by 8. And I'm not clear if UCIe is like PCIe where it's
No, you need to multiply it by 8 because it's 16 terabits per second. 16 terabits divided by 32 gigabytes.
Yes,
so
it's 512.
Okay.
It's 512. But I don't remember if UCIe is essentially half simplex or full simplex. Sorry, if it's simplex or duplex, I don't remember. And that's important because if it's like PCIe, then you would actually need 1024 lanes in order to deal with that bandwidth reads and writes. If it's not like PCIe and it's more like memory, then 512 lanes is fine. That's my point that I'm trying to talk about.
Yeah.
I don't remember off the top of my head which is which or what UCIe is. So somebody in the chat probably knows.
Well, what's the current shoreline density for UCIe?
I want to say I think.
No, but I'm not asking for actual numbers here. It's more hypothetical because you're gonna run out of shoreline.
Hypothetically, you could do it. I think that's the thing.
So I mean, it's not shown here, but one of the things I've been speaking to companies about recently is SerDes that aren't shoreline.
Oh, okay.
So yes, there is that. What's also not shown here is you can just about see it. There's an orange thing underneath the HBM5. And
Base die?
that is the base die of the HBM. So with HBM4, we now get an active base die, and that can do things like compression and security. And this is where some of the stuff's going to be differentiated in HBM4 land.
So speaking of that base die, and I'm seeing the LPDDR5X, which I assume by 2028 we will have LPDDR6 and LPDDR6X.
Well,
but
so that was actually going to be one of my criticisms when I got there. Why have they got 5X? The rest of the diagram is modern, is modern for the future, and that's a super old tech, going to be a super old technology at the time. But yes,
yeah. I wonder if they're putting the memory PHY and memory controller on the base die. On the base die of HBM5. That would kind of make some level of sense.
If there's enough space and if there's the logic to deal with a tiered memory solution.
Yeah.
So
I mean, if like we talked about, I think in the very last Tech Poutine, there is such thing as custom HBM. Maybe this would be an offering that Intel as a foundry would offer in conjunction with.
Well, so one thing that
vendors.
one thing that hasn't been kind of proven out yet is standard base die versus custom base die in the market, and we'll see that evolve as HBM4 evolves and as the standard gets ratified. But in this example, you have HBM5s around with LPDDR5Xs. And then on the right here, you have another EMIB-T connection, which goes, I believe, right. So we don't go straight onto the next slide. What they're saying here is that on top of that base die, because we had a T version, the TSV version, you're going to start stacking SRAM on top, like Vcache on top. And then on top of that, you have AI engines. So you have a compute base die, an SRAM middle layer, and then a compute top die, which is going to be interesting. And then you take two of them and put them together, and you get something that kind of looks like
Gregan Ultra.
So when this came on stage, another analyst leaned over to me and whispered in my ear, Falcon Shores.
Not quite.
But the sentiment is a future AI chip may look relatively similar.
Yes. Yeah, this looks like Gregan Ultra. I actually, if you still have that image of the product that they were holding up, the actual like
it's coming.
Well, no,
it's a thumbnail for the video.
Okay. But that package, from what I know, is actually a mock-up. That very one is a mock-up of the Falcon Shores. So yeah.
Raja Kaduri was at Intel's event. I didn't ask him. Yeah, and one thing that wasn't addressed was cooling. So between compute die and SRAM, IBM has a lot of patents in that area, and they don't use water, perhaps for obvious reasons. Let's go back. I wanted to bring up this slide. You have heard rumors, no doubt, that, I'll say this into the microphone, Nvidia is making chips on Intel.
Yeah, I mean, that's been a big rumor mill, yeah.
Right, so I can confirm that they are, but it's not for what you think.
I was not expecting it to be GPUs. Or at least not. To me, I was expecting it to be Tegra products. Personally.
So not even that.
Okay, interesting.
What so this is we all know that everybody speaks to Intel Foundry, right? Because
Yes.
talk is cheap. The government has put some money into making some of those talks real for
Okay.
government-focused things. So we have multiple projects from the government. We have RAMP, we have RAMP-C, Secure Enclave, SHIP. These are all different ways to help improve semiconductor support in the US for the federal government. And RAMP-C in the middle here is the one that Nvidia's involved in. So this is it, mask and fabrication with a nod to commercial foundry. So this is both helping the government understand the capability of the foundry and also getting some IP built. Not necessarily chips, but just silicon verified IP. And you remember those test wafers we were seeing before? It's that sort of thing. So you have Intel, Cadence, EDA, Microsoft, IBM, Nvidia, Synopsys, along with Northrop Grumman, Boeing, reliable something systems, and trusted whatever. So they're all coming together to essentially enable IP for the government on Intel Foundry. That's what that is. So when we say Nvidia is making chiplets or making chips on Intel,
what
it's
you
not
really mean is Nvidia IP is being integrated into IP that the government is building.
Or it may not even be Nvidia IP. Nvidia may be offering design services as part of this.
Okay.
Right? It's Nvidia is part of a government-funded research project to build chips with a dozen other companies.
So, in other words, this is not Nvidia moving away from TSMC. At least not as some of the media has been reporting it.
But if I write a headline that says Nvidia making chips on Intel Foundry,
oh yeah, big headline, big click.
Still technically accurate, but what people automatically jump to is wrong. So yeah, it's the same thing on the right here with the heterogeneous integrated packaging, right? The SHIP program with Raytheon, with Lockheed, with BAE. Understanding from a defense perspective what packaging means and assembly. How do we test government chips different, or chips aimed for the government or for fighter jets? You know, assuming the jet doesn't fall off the aircraft carrier twice in 1 week, which has happened recently, by the way, in the Red Sea. So yeah, it's that sort of thing. And then we get through, this is a second crack at the advanced packaging presentation. Just so yeah, like I said, S is like CoWoS S. Foveros R is the RDL based interposer. B, I say, is the bridge for design with voltage. You can put voltage regulators and inductors inside your bridge.
So there's rumor, based off some reports, that for Nvidia Blackwell, the bridges, the bridge that they're using between the two CPU dies, or GPU dies, excuse me, actually have DTCs, so deep trench capacitors, integrated. Did they talk about that for roast B?
No.
Okay.
You're talking about the embedded deep trench capacitors.
Yes.
That TSMC, and there was a slide at TSMC that spoke about it. I'm not sure. I don't think it was for modern process nodes. It was for future process nodes. But here's a slide about EMIB, offering better wafer utilization and what have you. And then we have here the TSVs in EMIB-T as well. Here we have that image again. This is on the thumbnail. This is Kevin O'Buckley. I spent about an hour sat next to him in a group Q&A, going back and forth. So that was fun. He was delightfully honest, but very knowledgeable. So he sounds like a good fit for Intel. Then we went on to some of the afternoon presentations. Here we have this defect density graph again. I went through that before you arrived, George. An 18A-PT, which we just show over. It's die-to-die bandwidth density increase of 9% here at the top is interesting.
I wonder if that refers to Intel 3T maybe not having hybrid bonding.
Yes, probably.
Okay, yeah.
But here's the graph. So I said earlier that 14A with high NA EUV is going to have a low NA EUV option, because we went through the math and basically said if you want a gigafab with high NA, you need at least 10 high NA machines in the fab in order to go through the wafer starts month. We factored in things like 3 layers per wafer needing high NA, also 75% uptime and all that. And when it said we needed 10, the thing is, what if you need to use a regular low NA EUV, which they've just described here as just EUV, you need, in order to print the same thing, you need 3 EUV exposures and 40 steps. Whereas instead, you could use 1 high NA EUV and below 10 steps. Thing is, you look at these pictures, and you can tell that the high NA is sharper. And part of building a chip is how sharp you can make the definition of what you're printing, but also how close you can get some of these parts. And Applied Materials launched a product last year called Sculptor, which does amazing things with that. It's a thing I need to do a video on at some point. And then this was interesting. So this is on one of the slides, and it got up, went away, and that's the face I wanted to see when I put. George, tell me the words that you were thinking.
Well, one, Ponte Vecchio.
No. Sorry. No, go back. What? I want you to say the thing you saw that slide is you then went, what chip is that?
Yeah. What chip? It looks like that looks like Ponte Vecchio, but it doesn't. It's a different chip.
So what we have here is it looks like two main compute die. And then we have some stuff around the edge, but there's this gap.
Yeah.
And then also on this side, it looks uneven.
Yeah. I think that might just be light reflection, but I'm seeing a mismatch of die, because if you look at that front edge, it's not even across.
Well, so this one at the bottom left could be like an XE tile.
Yes.
Sorry, the whatever XE link. Sorry, XE link tile. Then you have what looks like HBM, what could be a stiffener. The thing is, in Ponte Vecchio, there should be another HBM here.
I think there. Oh.
Is this is this like a reduced HBM version?
I think it's just like diffraction.
No, because you can see the underfill, right? There should be another chip here. So could it be an early spin of Ponte Vecchio?
I don't know, but it's. But here's the thing: look on the other side of that. Look on the other one, off to the right. You see,
it's not. It's not rotationally symmetric either.
No, and I'm not seeing the classic lines that you see with Ponte Vecchio or even Rialto Bridge. This is now I'm gonna have to go look at what this could potentially be.
For some reason, I was the only one that spotted that. So Davina says stock photography, and like, yes, stock photography, but of what?
Yeah, it's a stock photograph of what?
Yeah. So so we next time I'm in Arizona, here's a better image of EMIB-T with the through silicon vias, just showing what it looks like. On the left is how EMIB currently is. It's just a thing for high speed connectivity between. With EMIB-T, you can actually put power through it. Oh, Forgive God says AI generated image. No, it can't be. I mean, my camera being crap.
Wait, hold on. Check your Discord messages.
Yeah.
What is on the right there? I don't think it's that, but what is on the right?
Oh, test vehicle.
Yeah, it's a test vehicle, but that asymmetric packaging, right? It looks.
Here we go.
Yeah.
George, show me that. Where's this from?
This was from a paper on it. I don't remember which one. You
have to send me the paper, maybe we'll go through it. Okay.
I don't have the paper. I remember taking an image out of this.
Okay, we'll have to go find the paper.
But yeah.
So I liked this diagram. It means that we can truly think like Lego. Because I showed my quad peaks earlier about package sizes. So on the left, this one here, this is Intel's version of the 80 by 80, which is this 80 by 80.
What's interesting is that package is not Ponte Vecchio or Rialto Bridge.
Oh, on the left.
Yeah.
Yeah. No, that I think is actually a mock-up. And it's the
it looks a lot like B from the slide from that snippet that I sent you. It looks like B.
It almost looks like what they turned around and said something that Falcon Shores, when they first started speaking about Falcon Shores, that was a sort of diagram they provided. Or if I was going to be cynical, I would say this is what a HBM Xeon should actually look like.
I mean, you're not wrong.
Yeah. I threw up this slide on Twitter and said, if you can't tell the difference between advanced packaging, I feel bad for you, son. I've got 99 problems, but packaging ain't one. It's fun times. And this thing on the right, obviously super insane. But you gotta love it. Just don't ask about power consumption
or latency between the top left and bottom right dies.
Yeah. This is the power solutions, going back off what TSMC had. TSMC's event was first. So Intel showing similar things about how they're integrating. So you can't, I don't think you can see it here, but they have EMIB-T. So through silicon version
of
they're
Interesting.
inductors. No. So they've got EMIB on the left.
Sorry, I meant EMIM.
Yeah, so they're
MIM.
inductors. MIMS.
Not MEMS. MIMS.
MIMS. And then again, the deep trench capacitors, which is something they've been working on for a while. Do you remember they used to have notebook chips that had such big capacitors on the bottom, they had to cut out the motherboard.
Yes.
And they'd drop in back in the day. And then we have optics
Probably
again.
Do those predate me? Quite possibly.
No, this is more like 2014.
Okay.
2015. This is interesting. So one of Intel's advantages that they say they can do die sort, die prep, and they do singulated die tests. So even if you have a chiplet which needs its power from somewhere else, they can go and do test it. They've developed the design platforms to do that. I've been to Malaysia and seen it, or at least saw the version of it they wanted me to see. Which to the most cases like, interesting. Why is that an Acronix FPGA? What rather than an Altera FPGA in that machine and whatever? And a lot of it is custom. So, but the diagram here was a bit, they went through it kind of fast. But the idea being is on the x-axis, it's the number of die per package, and if you have a 98% yield, this thing here, the bottom white line, let me zoom in and move. As you go from say 0 to 25, 50 to 75 dies per package, your yield quickly drops below 50%. And we said this. If your known good die yield is 99%, so you have a 1% failure rate, and you have 47 die in Ponte Vecchio, your true yield, your yield after packaging, even with 100%, even with all good die being used, your packaging yield is only 62%. So you're losing a third of revenue just in packaging. Their argument here is because of their die sort, die prep advantage, and you can also bin match parts. You can get to 99.5%.
Okay.
So that's not a statement on yield off the line. That's the wafer that you get all the die off the wafer and test which ones work.
Now
and then out of the bucket of working die, 99.5% of those actually work. So your good die test does in of itself have a failure rate.
So, question, does that package or dies on package include HBM or not?
Yes, but you'd assume that HBM would be better. You assume that 99.9% of the memory you buy
is good.
Works.
Okay.
Right. It's all about if you get a real
really,
little
this
chips.
is about the actual logic silicon, for a lack of a better term, not the memory.
But you can apply it.
Here's where I'm gonna go. Cool technology. How useful is it actually? Considering that right now, I think our most chipletized part right now is MI300.
I mean, if you're taking Ponte Vecchio out.
Yeah, because Ponte Vecchio is no longer being made.
Okay.
So it's not being made, which leaves MI300 as the most chipletized thing, and it's only at most 13 chiplets.
And that's advanced packaging. There are some chips that just use standard substrate packaging, which are more like Turin dense. It's that sort of thing. The idea being is that if you take what we had ages ago, how many SRAM die were they going to put on the
on the
Right.
bottom.
Yeah,
I
or on the middle layer.
yeah.
So I actually have a hard stop in like 15 minutes.
Okay.
So this is the last slide. It was from one of the demos that they had at Foundry Connect. Am I blowing your mind again, George?
No, just interesting.
So they wouldn't tell me what cores they were using, just that they were non-x86. We believe them to be ARM. We believe them to be ARM. However,
ARM X, ARM A, 7, and A5.
No, so ignore that for a second, because it could be any. It could be any. It could be any. It's called Deer Creek Falls, and if you remember, the RISC-V test chips were all called Creek.
Yes.
Horse Creek was the one with Sci-5.
But there's
the one that
also other things that are called falls.
So falls may be the yeah. So we get into this thing of, is there consistency in naming? But Deer Creek Falls, this chip, I actually saw it in person. The aspect ratio is insane, and you can probably see that it's like a 3-to-1. But I don't. The last time I saw a 3-to-1 aspect ratio is in the I/O dies on my quad peaks, which is normally you don't have that high an aspect ratio on a chip because it leads to variation when you start dicing and stability. That's why most die are square or very slightly rectangular. But yeah, no, they had this as a system that was up and running. Unfortunately, I can't show you photos of that because I took a bunch of photos and then they plopped a big no photo sign in front of me. But this was up and running. They had 9 different applications running on this. One of which was Doom.
Of course, obligatory Doom.
But they also had like some image stuff and what have you. Yeah, and that was interesting. Just showing that this was meant to be like, we are enabling IP on our Foundry process, and here's an example chip to do that. But yeah, no, if as you said, it's a 1 + 2 + 4 design that kind of sounds like it's an ARM thing. There is a chance it could be RISC-V, but given the software used and what they were showing on it, I don't think all of that's ported to RISC-V, sort of thing. They also didn't say if it had it did have a PCIe GPU on it. I think it was like a 1050 or something. So it's something with a driver in Linux. ARM GPU drivers in Linux are a thing.
If it's an Nvidia GPU, then it's almost certainly it has to be ARM and not. I don't think there's RISC-V drivers available yet.
I mean, there's AMD drivers for RISC-V.
Yes, but not for Nvidia. And you're saying 1050.
It's yeah. Let's see if I can bring that up. Events. I won't be able to show it, but I should be at least able to confirm. Oh, maybe I can't tell because I've only got photos from the back and I can't tell.
Okay.
It's definitely like a 50 series class type thing. But yeah, no, it was up and running. It had a super small heatsink. So and yeah, I thought that was an interesting to see. There are other people who had. There were some other demonstrations about high performance liquid cooling and stuff as well. Yeah. So George, how are you? Good to see you.
Yeah, sorry, life happened. That's all I'm gonna say.
Yeah, but I know you had a few things you wanted to talk about, and I've kind of absorbed the full hour. actually, before we go on, let's go into some of the discussion questions on Foundry
Okay.
that we have here. How expensive are these wafers going to be?
Yes.
Yes. But
I mean, I would assume that they're going to be approximate to what TSMC charges, maybe more, maybe less, depending on capabilities.
well, I mean, even TSMC's new technologies I
Yeah.
spoke about before you came in. It's I think numbers were around what 18K last I saw for a 3 nanometer, about 24K for a 2 nanometer. You know, how soon are we going to hit it? The best way to think about it is go to a die yield calculator, and I'll bring this one up. I'll zoom in so you can see. Let's choose a standard smartphone silicon chip, 10 by 10, so 100 square mil. Yeah, and at $20,000 a wafer, that's $50 per active per good die. That's before you package it. That's before you bin it. And so how much does a smartphone vendor sell a chip for to the smart? Either
depending on who it is, but yeah, not
150, 200.
Yeah, for a top end chip, yeah, that sounds about right.
Yeah. So if suddenly we go to 50K a wafer, then we're not in smartphone. That the margin isn't there. So
yeah.
So that's the price of wafers. It's a good question.
Yeah.
So I spoke. I mean, you saw the Intel numbers. Some of these 20 to 30% gains. Are we expecting them to continue still?
Here's my opinion on it. I think we have to keep continuing it, whether we like it or not. It may take a bit longer, but I think those improvements will have to continue by hook or by crook.
That's the thing. Will they continue?
I think we're going to make them continue, if you know what I mean. I think they may take a bit longer, but I think we're going to still continue to see.
The physics is there.
Yes, I do think that we are eventually going to run into a limit, but I think it's later than people think it is.
So one thing I didn't touch on that I said I was going to about the Intel stuff. We all know that Intel bet the company on 18A.
Yes,
right? That was the whole big thing. And now Intel's announced 18AP, and they had a slide showing like all the IP verification and stuff. And we already know that they've announced Clearwater Forest on Intel 3 and Panther Lake. Sorry, on 18A, and then Panther Lake on 18A.
Yeah, if I remember correctly, Clearwater Forest is 18A compute tile and then a Intel 3 base tile.
Yeah. And then Amazon, I think an Amazon networking chip is going to be on 18A as well. However, from the conversations at Foundry, it looks like what Intel is doing is pivoting customers more towards 18AP. Foundry customers, not 18A. So even though AP is like a superset of A, as in more VT options, more tighter corners in the PDK.
Case, between Intel 4 and Intel 3?
Or 20A and 18. In the previous, it might have been called a plus, or the difference between N7 and N6, that sort of thing. But the timeline for AP is like 9 to 12 months later, or 6 to 12, depending on your error bars
Okay.
and what you want to do. So all the estimates about Intel ramping for customers on 18A,
Move
most
back
people,
by 9 months.
yeah, now they're talking about ramping customers on AP, and that
Okay.
and given what I've spoken to people building IP on these processes at big companies, and they say, oh yeah, no, the yield's good, the defect rate is good. Unfortunately, the PDK needs a lot of work.
I'm not surprised.
Right,
This
the simulation and the verification tools. Intel doesn't have experience in building those, so they've got a few teething issues, and it's making some of the IP designers. They're used to being
cautious.
comfortable. They're used to being comfortable with TSMC. They know what to expect. They don't know what to expect from Intel. So some of them
And
are
unfortunately,
saying,
that's just something that has to be borne out with time.
yeah, and confidence and experience.
Yeah.
So pushing all of that back 9 months helps with chip design. Some would argue it needs more than 9 months. The overriding question then is, does Intel have enough money to keep going? It's an open-ended question that doesn't need an answer, because we all know the situation Intel's in. And can they have a consumer products revival without it? Because ultimately, if the products team does well, Foundry can afford to be a bit where it is right now.
Yeah.
Mid.
So,
Some would say that's generous, George. But
look.
it's for everything I'm hearing says that it's a good process, but the ability, as in when it works really well, but because of the PDK, or at least because of the accuracy and the simulation verification, it's a fine line to get it right first time. I'm not sure whether it's throwing a dart in a pub with your offhand backwards and getting a strike in the skittle alley sort of thing. But it's to your point again, predictions get pushed out another 6 to 9 months as a result. It does mean that people are being one of the common comments I got all the time was, why aren't you announcing customers? Is it because you don't have any? To which my response is, does TSMC ever announce customers?
Customers announce. TSMC doesn't announce.
Yes.
The only exception to that is when it's like the AMD TSMC announcement, where it's a joint announcement. But that was really driven by AMD, not TSMC.
Yes.
Because you have to remember, that announcement is not on TSMC. That's on the customer.
Yes. So so people complaining at Intel for not announcing customers, my response to them is turn around and say, when TSMC announces a customer, we will. Because TSMC won't announce customers. Now, if you go to their museum, you'll see chips from customers.
Yes, but those are already announced and out, and stuff that already exists, not stuff that we know.
Yes,
not unknown.
Yes. So Intel's getting raked over the coals for not announcing customers, specific customers. They might talk, and they announced last year that one customer had $1 billion prepayment, that sort of thing.
I think that was AWS.
Yeah. So, and we only know that because we browbeat it out of them.
Well, no, because I think Amazon announced that in September during the Granite Rapids launch. When that came out.
The thing is, one of the Graviton chips used Intel packaging anyway.
Graviton.
I want to say 2,
3, and 4 both use EMIB.
No, I thought they used Intel standard packaging.
I'm pretty sure that Graviton 3 used EMIB and so is 4 but they're using less EMIB for 4.
Okay, yeah, I'm getting confused between.
Um.
Oh yeah, okay, yeah, that's right. It's hang on. Let's cut here. For those wondering, so this is. Can I get just that one? Yeah. Just that image. So you got Graviton 1, 2, 3, and 4 here. That's a really nice image, actually.
Yes, it is.
For some reason, I had thought that the connected ones here were just normal packaging like the other two.
No, it's advanced packaging. If I remember correctly, the close-in tiles are memory and the outer tiles are PCIe, which makes sense when you consider that PCIe is
memory controllers.
Yes. Sorry.
Yeah, memory. Yeah. To be honest, Ampere does almost something similar.
If we had more time, I would.
It's not. It's
they
standard
just announced
packaging.
A new product, so.
Did they?
Yeah, they announced Ampere. Ampere Computing announced the Ampere 1-M chip with 12 channels of DDR5 like 3 days ago, but they didn't send a press release out to anyone.
There might be a reason.
They basically
for that.
made a tweet, and that was it.
Okay, I'm gonna have to catch up on that. But yeah, so it's they get reamed for not talking about customers. So yeah, okay, we've got 10 minutes left.
Okay,
I'll go over 10 minutes. So George, what's on your mind?
So okay,
yeah, so this is your time. If you want to choose a topic in the document we have, or if you just want to talk crap.
Yeah. I think I warned you of this last night.
Yeah.
So, I've been disappointed. I've been frustrated. I've been exasperated with companies, but I don't think I've ever truly been angry with a company. Until
I've seen you angry at a company, so this must be pure, white-eyed rage.
But yes, this is true blindsided rage, and it's with regards to the 5060, and how Nvidia is not releasing a driver to the press for the 5060 until May 19th, which is the day of launch. You know where basically everybody in the media is going to be on May 19th, Ian?
Dell Tech World.
No, Computex. Everyone's going to be in Taipei at Computex. And Nvidia knows this very well. I'm sorry, Nvidia. This is unacceptable. This is blatant anti-consumer BS.
Sorry, no, they're going to be at Google I/O.
Yes, but as much as you and I guess I can't really speak for you, but we've talked about how there are some issues in the media, definitely. But the media is how consumers and the average person can make purchasing decisions. It's based on the data that we provide and the data that is gathered by the press before release.
So 2 things here. One, how many people buy a 60 series on launch?
Lots.
On launch.
Lots.
On launch.
Lots.
Not enough. how many are going to be available at launch?
The answer to that is probably not enough. That I will give you.
How many get sold to home builders versus pre-builts?
So that is yes, I agree. The large majority of 60 series cards and 60 series equivalent cards are sold to OEMs for selling at Best Buy or Walmart or Costco in a OEM desktop system.
I would say it's probably a good 80 to 90% of all
Yes.
60 series sales are on pre-built. So I go back to my first question. How many get sold on day of launch? Because they're not going to be in pre-builts
To
yet.
DIY, probably not a ton, but every single one of them will be sold to someone.
That might be more of a reflection of the current state of the GPU market and the macro,
Yes.
rather than it being a competitive part that needs analysis. So I'm not trying to defend Nvidia here. I should point
Yeah,
out.
no, I know.
This is me just walking through the motions of understanding market
Mhm.
dynamics as I play with my fidget spinner.
Gen Z, we have become, have we? But
totally lit, bro. Skibbity Ohio. It's so I've I'm not saying everybody should do this, but I have literally benchmarked and reviewed hardware while at Computex. It wasn't the 10900 KS, if I remember correctly, launched that week. They seeded no one. I bought it. It was a 9900 KS or something. I bought it at the Guanghuan market for about $500. Retail recommended retail price was like $450, so I overpaid to get it. I then went to ASRock on the show floor the next day.
Asked for a board.
No, I said, "Can I borrow a system?" Because I had none of my. I asked for a board, but I didn't have a power supply. I didn't have this. Didn't have that. And they gave me a system. They literally in the afternoon, as the show was closing, gave me a system, and they said, "How long do you want it for?" I was like, "Give me 48 hours." I think I gave it back at the end of the Friday. The show finished on the Thursday. I was flying out Saturday or Sunday or whatever. And I had that review up. I was the first person to have a review of that chip. Because everybody else was in the middle of flying home. Now, I have taken power supply, motherboard, monitor, keyboard in a second suitcase with me to Computex before, because I had to benchmark while I was there. I'm some of the most, back then I was insane. And on top of that, also putting out 50 to 60 news posts and having 50 meetings. And luckily I had my benchmark suite with me, and it's automated. So I just made sure it booted up. I got all my BIOS images. I did some just minor testing, and then I can just click play, go. I didn't have it set up so that I'd have a text message that if it went wrong or whatever. But I could come home at the end of the day and my benchmark suite would be 70% complete. It would only be the super long compile tests left. And then I'd put a GPU in. I think I managed to get a very similar GPU to the one I use at home. So yeah, different memory, but this is one of the reasons I set it to stock, right? For my testing. I had a very similar GPU. So it's a different motherboard that I tested, the non-S. But it's possible. Are Nvidia actually sampling hardware though?
Nvidia did not, but the OEMs did.
Yeah,
OEMs seeded. And that's the thing. OEMs have already seeded the hardware. But apparently Nvidia is not giving the driver. So it's not quite the same case. It's I feel personally as if this is Nvidia thinking that they can at least delay review of these cards and there will be no pushback.
It's such a small part of their business.
That's what's getting me, is I don't understand it. Like,
yeah, you mean it's such a small part of the business? Why don't? Well, no. So my thing is, it's such a small part of the business. They don't care what event's going on. So it's not an issue for them because it hasn't even entered their mind. Your response is, it's such a small issue. Why not do it right?
Yeah, like move the embargo to before the card launches, or make it after Computech. Like, I don't get why they're playing what feels like games with the media for this launch at this time.
No, because Nvidia's not a gaming company. They don't play games. Sorry, that's pretty bad. It's yeah. So same thing. Never pre-order something. Never buy it on launch day.
Always wait for reviews that you trust and wait for multiple people to review, ideally, so that you can get a wide smorgasbord of data that the viewer can then process.
The thing is, we know the specifications.
Yes.
We know at a high level roughly where it will fall. Right?
Yes.
What the reviews tell us is, are there any major flaws? And if that was your concern, you're never going to buy it at launch anyway.
Yeah.
So
just
it from a 30,000-foot view, it looks like a storm in a teacup. For everybody close, it's a big outrage. I
was so much more animated last night. I was very angry when I heard the news. I have since slept on it and had some stuff happen, so I'm much less animated than I was last night. But I'm still very upset and angry with this.
What's the pricing on it?
This doesn't 300.
Okay.
But I hope that this does not set a precedent for Nvidia in the future, and that
it's every company has had really crappy launch at some point.
Yeah,
right.
True.
So just like I said, the KS chip that I reviewed, that had a really crappy launch. Stuff that arrives on Thursday for a Monday launch. I know peers. We have peers around my age who have been in this industry enough. Now they don't pull all-nighters or all weekends anymore. If they would rather take the hit of not being first in order to just have better family life. So, and with that, I do need to call it a day. The next week, Poutine probably will have to be Wednesday, I guess.
Okay.
Yeah. Next week might be Wednesday. And then we have Computex.
And I do sincerely apologize for being late. Just stuff happened.
It's all right. It happens. Yeah.
Usually I'm not late. Usually if I have a prearranged meeting, I will be on time. This is more of a fluke than anything.
Yeah. I will say we were thinking of doing this one pre-recorded and then putting it up as a premiere. George and I still need to talk about it. If any of you have thoughts on that, like a yay or nay, or it matters, it doesn't matter, let us know. I know some of this show we do interact with the audience, so in that case we wouldn't be able to. But sometimes our schedules just don't work, and it may make sense just to record them, some of them. in the future. So we're thinking that that might happen, but we should be doing one from Computex, which means we'll be at the wrong time zone for everyone. So yeah. But good to see you all. Let's go get some dinner. I think.
Have a good one, folks.
Yeah. Oh, we did have an exit hatter, did we? Oh no, it's gone. Okay. Yeah. All right. See ya. See you next week. If you like this content, there are multiple ways to support the channel. You can like and subscribe this video, and many thanks for doing so. There's also a Patreon, which gives you access to our Discord. There's a merchandise store and a newsletter, links in the description. For all of you who do contribute, thank you. You are keeping me well fed.